So I'm just, okay, so this is mainly for Chris in Philippines. So Chris, we have decided to extend the homework for one more week for the coding first coding homework. But as the extension, we also want to add a little more to the homework. So I'm going to explain to all of us what do we need to add more. Okay, so give me 1 second, open up. So so in last homework, we have talked about a solution basically. So if this is the f function, which temperature right now as we speak, let me just use this, and this is x-axis. So what we want to show is that we have a curve like that as a true solution, and supposedly now we have a approximation goes like this, and goes like this, and goes like that, and that, and so on and so forth. Excuse me, guys, give me 1 second. Something happened in my living room. Just 1 second. All right, guys, sorry, I'm back. Something happened in the living room. Okay, so these are the lines data where we call it finite element solutions, right? So now, if you trying to find errors, right? What we can do is pick at least 5 points within each element. Okay, 5 points within each segment. All right, so on and so forth. And I want you to do an error of sigma error at these points divided by total number of points you have. Okay, so let's call this average error. All right, and I want you to plot is this. Say if, just use a different color. Say if this is the average error. And what you're doing is you're changing number of elements in the homework. Okay, and I want to see that, right? It's how this average error changes, right? Did it go like this? Did it go like this? Did it go like this? So anything. Okay, so you may ask, okay, as your computation increases, right? So what is the maximum number of elements you can change? So we said sometime last time we set a limit on the number of elements. So I'm going to reset this limit, increase that to say 100 elements. Okay, so you can pick say 5. Well, actually, just be very precise. 1, 5, 10, 20, and 100. Okay, so these are the elements that we want to see how the error changes. Okay, so these are the added homework. So added to homework number 1. All right, so Alfred find access to MATLAB. I think Hytham, do you have access to MATLAB at all?
Yes, I have access to MATLAB.
You do, right?
Yeah.
So Jody and Moy, you guys don't have access to MATLAB, is that right?
Yeah.
Not right now, okay.
Yeah.
So there's a computer room in the first floor in our BCH building. This first floor, you see a lot of computers.
Yeah.
Okay, so they should have MATLAB there.
Okay.
So try that. I would say that it's Friday afternoon or somewhere over the weekend. You guys should have access to it and turn it on to see if you guys can access MATLAB there.
Okay.
Yeah, if they don't allow you to have access on the computer or they don't have MATLAB installed, send me an email over the weekend.
Okay.
Yeah, so let's extend our deadline for the first homework. Say extension homework new due date. Say October the 1st. Okay, and I'm not asking much. This plot is from homework number 1 already, right? So homework number 1. already given. And these are new plots. Only added one more plot basically. Okay. So error changes as number of element changes. Okay. All right. So that's that for homework number 1. Okay. And I'll post the homework number 1 on Canvas so you guys can submit through PDF. So the way I want you to submit the homework is this way. I want you still write the homework up. Alfred, you there? Are you there? Can you hear me? Alfred?
Yes.
Okay, so you have done it already, right? But what you sent me is just a bunch of plots. Is that right?
Yes.
So I want us to do this way, and no harm done, and you don't know the rules and all. I haven't talked to you guys in detail. So I want you guys to do this way. So you have a problem statement. Okay. And now you guys are graduate student, not under. So I'm going to ask you guys to write the problem statement yourself. Okay. So there's key elements you need to write for the problem statement is that 1, what equation we're solving. Okay. Governing equation, you can see from the code yourself, basically helping you to read the code. Okay. And what integration scheme, quadrature, basically method you guys are implying. Right, so this is specifically quadrature. And more specifically, how many points? Okay, and then 3, 2, so what are we investigating, right? 2 points. Sorry. So 3.1, these plots, right, is to show error distribution.
I'm sorry, Dr. Wu.
Yeah.
I cannot see your screen. I think it's frozen.
Okay, let me reshare it. Can you see the screen now?
Yeah, I can.
Good.
Thank you.
Yeah, sure. So first thing is what equation we're solving or are we solving? My grammar can be mistake. Sometimes help me correct it. And what integration scheme do we use? All right. And then 3.1, this is show error distribution, right? Then Alfred and for the rest of the folks, all those plots should be here. Okay. And Alfred, if I understand you correctly, what you did that you simply plug in the number elements and see all kind of plots, right? You didn't change the code. That's what I mean, right?
Yes.
Okay, so I want you to show a line where the element input is. Okay, simply just copy paste that line. Start with a pound mark and do like that and copy paste and that's it. And then I want you to show the temperature as number of elements increases. So however number of elements you use for the error distribution, error convergence in the 3.2, you show it here. Okay. So 3.2, I want you to show convergence. Needless to say, you will know that, okay? You will know that the average error, as I told you how to define average error, should go down like this. Okay, and now don't stop here yet. When the error goes down like this, okay, try to fit a line here. Okay, use polynomial. Okay, and I want you to show me what is the power of this fitting line here. Okay, what the power of this fitting line here, and then last but not least, compare this power with number of elements. Okay, so this is the total number of elements, right? Then let's say last. And I want to see, just simply put it down here. When you fit the polynomial, right? find the best fit, of course. You will find the best fit yourself, right? And tell me what is this number here. And trying to see if there's any correlation with this number here. So you say, Bob, you know, this is only a fixed number. So M is also a fixed number. How, what is the comparison? What are you talking about? So I want to do this, right? So you can do multiple fitting lines. If you say I stop with this n equal to 1, n equal to 5, I'm just making things up, 10, 20, right? Then you truncate here and just fit like this. And you get M, right? Then you go on and say n equal to 30, maybe 40, 50, 60, and then you truncate, say 50. You fit again because you have more data now, right? And then you have a different M. So eventually what I want you guys to show me is that plot number of elements, total number of elements you have for the error distribution chart. So this cannot start from the very one because you don't have a fitting. So maybe n start, I don't know, I'm making things at 10 here, 50, 60, I don't know, 100, right? And I want you to show me that when you fit the error distribution, how does that M changes, or does it M changes or not? Is this like that? This is like this, or straight line? Okay, all right. And if you're smart enough, well, I hope so. I think you guys are all smart here. And then comment on this relationship. Okay. So if you're curious, you can also Google it. Do some research, right? Find out if there is any theoretical linkage between the fitting of error power of M and number of elements N. Okay. So these are the homework number 1. Is this clear, guys? Any questions about it? Folks, anything? Are we okay? Come on, don't be all quiet, right? Tell me if it's okay, if it's not okay. Any questions on this?
It's
Yeah,
okay.
it's
Yes.
okay.
Good, okay. Alfred's good. Jolly, okay?
Yeah, I'm
Okay.
okay.
Okay, so I'll post this, you have this, okay? But I want to organize your homework. Don't just show me a bunch of plots. There is a meaning of doing this homework. Well, let me be frank. I'm trying to make this course as easy as it can be because you guys all graduate students, not under. You guys all have other assignments and you know what you need from this course. You need to have a good understanding of it. So what I'm trying to do is more like help you organize your thought process and let you see the internal machinery of the finite element. So when later you apply the finite element, you know what you're doing instead of just hitting the buttons and trying to get some numbers. Okay. And once we get a homework number 1 back, I'll grade it and I will discuss these results with you more openly. Okay. All right. So hopefully we're fine with the first homework, and the new due date is October 1st. Okay. So no stretch, don't sweat. Okay. Just take your time, try to understand a little bit more, and give me a best homework. If we need more time by October 1st, we can talk about it, or I can talk to you about a problem. Sorry, homework number 1 in details. But I like to set a deadline so you guys have some time frame to work on it. All right. Okay. Okay. So let's continue. Okay. So lecture number 7. Today, we're going to talk about a different elements. Okay. So let's try just draw it out. Okay, today we're going to talk about this fellow, 4 node. Okay, 4 node elements. Okay, and also we'll talk about an 1, 2, 3, 4 in case I lost my count, 5, 6, 7, 8, and 8 node elements. Okay, 4 node and 8 node elements. All right, and in Abacus you have name for this. Okay, you have name for this 4E, 8E, or something in front of it, okay, and we can talk about that. All right, so first thing first, 7.1, let's talk about the 4 node elements, and this is terminology is known as linear quadrilateral element. Okay, quadrilateral element, so Q4, right? Or in Abacus we call it Q4E. Q for E means elastic, okay, elastic. So we have talked about triangular elements, right? We all know there's a coordinates, everything, right? So imagine I have a global coordinate system, Y and X here in 2D, okay? We're still in a 2D domain, two-dimensional domain, okay? Now I have an element and it looks like this, very weird shape. I have 4 nodes and simply connect the lines between them, okay? And this is a local element, right? So I want to make things easier. So instead of using the global coordinate system, I'm going to use the local coordinate system. So just go like this. All right. So if you haven't noticed how I drew the line, it's not arbitrary. I connect the center of these 2 nodes with the center of these 2 nodes. Again, center of these 2 nodes, center of these 2 nodes, and draw the line like that. Okay. Now, the question is this perpendicular to each other? The answer is not necessarily. Not necessarily. Okay, by Cartesian coordinate and by Cauchy coordinate system, that as long as we have an orthogonal coordinate system, we can represent it exclusively. So when we have non-orthogonal system, what we have to do is we have to attach this local coordinate system with an orthogonal system. That is, we need a transformation matrix. If you don't remember last lecture, we talked about it, we need a Jacobian. Okay, we need a Jacobian. But right now, let's don't worry about it. Okay, so let's just say this is Xi and this is eta, 2 axes. Now with each of the node, let me just start naming nodes. This is 1 and 2 and 3 and 4. Remember, it's always counterclockwise. Okay, when you're naming the nodes on the elements, always counterclockwise. All right, now for each node I have displacement. So this is U1 and this is V1, this is U2, this is V2, this is U3, and this is V3, and again U4, V4. So UV representing the displacement along X and Y direction. Okay, along X and Y direction. And for that matter, we can also say along eta and Xi direction. Eta and Xi direction. Now, XY is we call it global coordinate. Eta and Xi and eta, we call it local coordinates. And the relationship between XY and eta Xi system is that XY is a projected or can be projected from the eta and Xi through the Jacobian matrices. Okay, through the Jacobian matrices. Okay, now I'm putting an operation dot in front of it. This does not mean it's multiplication. Okay, it just means operation, J operation. Okay, and we can talk about that later. We can talk about this later. Okay, now for this, we also need to have coordinates, right? So when I put Xi and eta, in my head, I know that when this is Xi, this is Xi equal to -1, this is Xi equal to 0, Xi equal to +1. Same here on the top, this is Xi equal to +1, Xi equal to -1, and Xi equal to 0. So before I know it, I have 4 nodes mapped out. So node number 1 is what? -1, -1. Number 2 is what? +1, -1. Number 3 is what? +1, +1. Number 4 is what? -1, +1. Okay, and be careful. These quadrants are different from the regular Cartesian system. And this is for a reason, okay? We'll talk about this, but this is for a reason. Now, with this, I can start write out the shape functions now. Now, within the local coordinate system, within the local chord, my shape function looks like this. And 1, which is shape function associated to node 1, equal to quarter of it, 1 minus Xi, multiplied by 1 minus eta. And 2 equal to 1/4 quarter of it, 1 plus Xi, 1 minus eta, okay? And then in 3, 1/4, this is 1 plus Xi, and this is 1 plus eta. And 4 equal to 1/4, and this is 1 minus Xi, and 1 plus eta. Now these are my shape functions. Now, once I have shape function, I need to quickly check it. So how do I check my shape function? I need to know that Ni, when I equal to this node equal to 1, and when I does not equal to this node equal to 0. Okay, I need to check that. Of course, what it's saying is that when X, or when you're sitting on particular node, this is 4, and 4 would equal to 1, and the rest of it should equal to 0. Okay, so in your head, you have a 3D image like that, right? So N1, N2, N3, etc., etc., etc. So with the shape function, quickly I discretize my field. Now displacement in X direction can be rewritten in terms of a shape function that is for an I UI. And V equal to what? For an I VI. Okay, so that, ladies and gentlemen, is my linear equations, linear functions. Okay, so this is not bad, isn't it? This is not bad at all, right? So now I look at this element, I say, look, I have discretized my element into 4 nodes of displacement. How about I solve my elements? How about solve my elements? So I want to solve an element, a simple problem to start with. So how do I start with a simple problem? So first of all, I have an example, right, of boundary force handling, or boundary force distribution. Okay, why do I need to consider this? Simply because, say now I have an element 4 node, element like this. Okay, and in finite element, what we do first is this is called element verification. What is element verification? When you try to build element, code an element yourself, it's first thing to do is not build a solid body. It's just focus on one element and apply forces to the nodes to solve the element. Is that right? So that's something we need to do first. But in a case like this, right? So this is 1, 2, 3, 4. I want to start solving a very simple problem. I say, look, if I have a distributed traction, like this alongside 3, 4, alongside 3, 4. All right, and then let's call it QA, or sorry, Q4, because it's acting on 4, and this is Q3. Okay, and then it follows certain distribution between Q3 and Q4. And now I have this stress or traction acting on it. So how do I solve this element? How do I solve this element? Okay, so I'm gonna start asking questions now to keep you guys awake. Okay, Moin, are you there?
Yes.
Okay, so you have the problem like this, 4 nodes element, you have a distributed stress on it. So how do I solve this element? So simply put, what are the unknowns within the elements?
Mm.
Okay, I know this is a little bit difficult because it's jumping too much. Let's take it slowly, okay? So for a 4 nodes element, Moin, how many degrees of freedom?
For each node,
For all of them, right?
we have 8
Right,
displacement, and I think for
that's it, right? 8 displacement. Okay,
Mhm.
when we say degree of freedom is usually in terms position or location in space, right? So what I'm trying to say, if you know the nodal displacement for all the 4 nodes, the shape or the position of the element is fixed.
Mhm.
Displacement field is also fixed because you have the shape function interpolate within the element. Is that right?
Yeah.
Right. So that's correct, degree of freedom. And you're not off the hook yet, Moin, right? Let's continue.
Mhm.
So I have 8 degree freedom. So essentially what I'm trying to solve is, help me out here, right? So I have a K matrices already, you know that, right? So K is going to be 1, 2, 3, 4, blah, blah, blah. How many here? How many?
8.
8, exactly. So I have 1, 2, 3, 4, it's a square 8. So here I have what? U1, V1, U2, V2, and how many I have here?
U4, V4.
Right, so 8 again, right?
Mhm.
Good. So these left is 8 by 8. Is that right? Matrices, K matrices,
Mm-hmm.
right? So you learned that from previous fine. And displacement is 8.
Yeah.
Is that right? So right on the right-hand side, what are these? What are these? These are nodal
Forces.
forces, right? So
Mm.
how many I got? I
8.
need to get 8 as well. Exactly. So that means if I want to solve the problem, eventually I need to know that what is the nodal force
Mhm.
on each node. Is that right?
Yeah.
Right. So question I have is that, do I know these nodal force or not?
Mm.
Do I have them not? Do I have them yet? No, QF actually. Sorry. Do I have any nodal forces as you see it from the problem? I'm just indicating, right? They're not there. I'm just indicating. But do you see any nodal forces yet?
Mm.
Yes or no?
I really don't know.
You don't know, right? Now
Yeah.
let me to say it. I only see an element, the blue ones, right? That's the original element, right?
Yeah.
And I applied a blue one, distributed stress on one side of it.
Mhm.
Is that right? But I did not have any concentrated force on any of the nodes,
Yeah.
right? So the answer is no, I don't have any nodal forces in this setting. Is that right?
Mhm.
Right.
Yeah.
All right. So Zhao Li, are you there? Are you there?
Yeah.
Okay.
Yeah.
So quick question here. I have K, I have U, and I have 0 nodal force. Is that right?
Yeah.
So if I have 0 on the right-hand side, whatever K might be, I try to solve for U, right? And U equal to K inverse multiply nodal force F. Now F is 0, what I got for U? So U is displacement equal to inverse of the stiffness matrix multiply the nodal force F. And I know that there's no nodal force, right? F equal to 0, what I got for displacement?
Mm.
Something multiplied 0 equal to what? Anything multiplied 0 equal to what?
Mm.
When you do mathematics, right? You multiply anything with 0, you get what? It's not a trick question, Zhao Li.
Maybe
Anything multiplied by 0, anything do this multiplied 0 equal to what?
0.
0, right? So they're right. It's not a trick question. So what I mean by that is, if this is 0, I got displacement equal to 0. That means what? Means I don't have any displacement on these elements. Is that right?
Yeah.
Right. Now the problem is, do I have stresses or tractions exerted on side 3, 4? I do, right?
Yeah.
So do you think, does it make sense that the displacement field of this element is 0? I mean, is it correct? Yes or no? Just instinct, basic instinct, not a trick question. Yes or no?
Yes.
Oh, so if I have stresses acting on an element, there won't be any deformation on the element?
No, no.
No, right? It doesn't make sense, right? So
Yeah, yeah.
that is to say that the nodal force cannot be 0,
Yeah.
right? So that's the answer of the question, right? So Alfred, are you there?
Yes.
Yeah, let's
Yeah.
think a little bit together, right? So like I just said, there's no nodal forces now. And I have tractions on one side, and it doesn't make sense because I need to have nodal forces. So in this situation, how do I solve my displacement? There must be something, right, to give
Yeah.
to the nodal forces. And how do I do that? By instinct. How do I do that? So how do we, before you answer, right, I give you some hints. So remember how we did this. This is what displacement field equal to what? N what? Ni ui, right? Is that right? That's the discretization. Is that right, Alfred?
Yes.
Okay, so what if, right? I look at this as, what if my nodal forces, right? Or my let me ask you, the displacement is a continuum field, right? Every point I have displacement, not only on the node, everywhere inside the element I have displacement, is that right?
Yes.
Right, so if I have Q, which is stress that in the space, right, equal to something like that, that would solve my problem, isn't it?
Yes.
Right, right. So what I'm trying to say is that when the old fellows, when the founders of FEA thought about it, so what it is that they follow the same discretization scheme. They redistribute the distribution of the loads and convert that into nodal forces. All right, convert that into nodal forces. So how do I do this? To do this is actually a long story. To do this is actually a long story. Okay, so let me ask you this. What is the equivalence between the distributed load and the total force? Simply integrate, right? So integration of Q, this Q is not right? Because these are not right-hand side is the total force, left-hand side is distributed, right? So I need to integrate the boundary, right? And let it equal to the total force, which is summation of nodal forces, right? So they have to be equal. But this is called equilibrium in forces. All right. So what's more important is that we need to trace the work done to establish this. So this equilibrium in force, and we need to trace the work done to establish this force equilibrium rigorously. And thank you, Alfred. This is the end of the question. Yeah. Thank you, rigorously. And Heiterman, you're probably shaking right now, right? You know you're the next.
Yes.
Okay, right. So I'll save the best question for you, okay?
But I have a question, Doctor.
Go ahead.
I understand now if you want to get this the force in the element 4-3, we can multiply the stress by the cross section. The cross section is constant, right? If you
See,
know the
that's a good question, but think about it. When you have stresses exerted on the side 3 and 4, right? The displacement of 3 and 4 will change because you're stretching it, isn't it?
yes.
So when you change the nodes, you change the area of the element itself, isn't it?
Okay, so the area now is changing.
Right. So you cannot use the area to just simply give you the total force on the element. What you're talking about is assuming the element's a node, you're doing this.
Okay.
But the elements changing is varying all the time. Get it?
Okay.
Yeah, yeah. So cannot do that.
Okay.
Okay. Well, we thought about it. I mean, all you guys are seeing right now, it's not like a flash of a thought. It has been going on for ages, and people just thought about it, like a better thing to do, I guess, you know. So that's how you do it. Okay. All right. So let's do it, right? So now, what I'm going to do is I'm going to look at it this way. I say, look, essentially, I only have this bar, 3 and 4, that have the distributed load on it, have the distributed unload. I say, never mind, I'm going to start doing distribution. I'm going to start to summarize the work done by this. So the work done by this is, say, big WQ, and that is integration 0, okay? Multiply, sorry, to the boundary of what? To the boundary of L, which is the total length of the bar. Let's just say this is length of the bar, and that is changing, okay? That is all time that is changing, okay? 0 to L, and then I say the displacement on the boundary, and then the traction exerted on the boundary, and then do the integration. Now, this displacement is not any displacement, is the projected displacement along the same direction of the projection displacement along the same direction as Q. So that is the work done by the forces or by the distributions. Okay. So I have displacement now, I have traction now. So displacement US, right? To differentiate, I put an N as a normal, right? This displacement can also be what? Discretized. Remember, it can be discretized into this, right? Now, this displacement is only happening along the side of 3, 4. So it has nothing to do with node 1 nor node 2. It only has anything to do with 3 and 4. So I can quickly discretize it into 1 minus S over L multiply UN1, sorry, not 1, 4, 3. So this is 4 actually on the left-hand side, 4 plus S over L UN3. All right, so that is the displacement field. Okay, now with this displacement field, same thing as I said before, how about the traction? The traction can do the same discretization, right? It can be 1 minus S over L and then Q4 plus S over L QB, Q3. Okay, so that has been discretized. So instead of finding the exact stresses along the side 3, 4, I use the nodal traction has 0.3 at 0.4 to approximate it. So now I have a total work done omega Q equal to the integration of this. So when I do integration, I discretize same time, right? So this is UN4, this is UN3, and inside the matrix is here, I have 1 minus S over L, S over L. What is S? S is simply the variable, right? Assuming S is from 0 to L, okay? And this is that, and then multiply whole thing, 1 minus S over L, okay, bracket, and then this is Q4, and this is Q3. And the whole thing ds, integrate, okay? Now, after integration, I mean, this whole thing, this is constant, put the constant out and do the integration inside the bracket, right? And then I got is omega, so big WQ equal to UN4, UN3 in front of it. And then I have L over 6. And now I have 2, 1, 1, 2. This is Q4, this is Q3. So this is work done by Q along 3, 4, alongside 3, 4. Okay. All right. So that is the total work done. Okay. So now I start look at it. If I have an element that is like this, right? And I have a distributed load like that, and this is 4. 4, 3, 2, 1, and this is 3. I'm just drawing it, right? So there's a distribution of that. I want to convert the left element to a element that does not have distributed traction, but only have nodal traction, nodal forces. Okay, so I need to make sure that this work done is the same as this work done. Is that right? All right. So notice that these are just displacement at 2 nodes, right? So let me ask this question, Heiterman. So for the right element, this element right here, right? So I want to write out the equation for work done here, omega Q, and in front of it, this is UN4, UN3. Of course, these are just displacement at node here, node here. So now I need to write here, right? So what do I need to write here? What do I need to have here, Heiterman? What is the work done? Work done is force multiplied distance, right?
Yes.
So I have a displacement here, UN4. So what I have here?
Force.
F what?
F3 and F4.
F4,
F4,
right?
F4.
F4, right? So because
F4.
this one multiplied by this one gave you the work
Yes,
done by
F4.
this node, right? So this one is what?
F3.
There you go. So on the right hand side, it's extremely easy. I have 4 nodes. Each node will give me the work done, and I have displacement UN4, UN3. All I need to do is multiply 4 and 3. So now observe the left and right, right? So I put this sign here. UN4, UN3, and this whole thing bracket. Let's just say something, right? And now drag all the way here. And what I realize is that this fellow here is the same as this fellow. So canceled. All I have is what? All I have is, I know for sure that F4, F3 has to equal to what? L over 6 to 1, 1, 2, Q4, Q3. Is that right? Q4 and Q3. Okay. So what is Q4, Q3? Q4, Q3 are the distribution of traction at node 4, distribution of traction at node 3. Okay. And this is only for a linear distribution. Okay. This is only for a linear distribution. Why is that? Because I use the linear approximation here. That I use linear approximation here. Okay. Now, what if my distribution is nonlinear? Like that. Okay. What if my distribution is nonlinear? Jiao Li, are you there?
Yeah.
Question is, what if my distribution is nonlinear? Can I still use the equation here to approximate my traction distribution?
Yeah.
Yes, right? That's the correct answer. Why is that? Why yes? Because when I trying to do this, all I care about is the total is the same, isn't it? This is the same as the FEA approximation. Okay. All right. So you need to know that. Okay. So the discretization of traction or conversion of traction along the sides into nodal value does not, let me say this again, does not depend on the shape of the real distribution of the stresses. It only depends on what? The shape function of the element. All right. Very important. Okay. So what does that mean? It means that if I solve the problem, right, with the element, okay, whether you have, unfortunately, if I have two elements, okay, this is practical sense to you. If I have two elements, one have a distribution, say Q, and this is 2Q, and these are Q are constant, okay? I have this exerting on 4 node elements, and I have the same element, identical elements, okay? And then I have Q, same nodal forces, sorry, not distribution of traction, but instead I have this distribution. And what you end up with is that what? The displacement you solve for this is assuming just have U4, U3, and U4, U3. And this is for Alfred. Alfred, you there? Alfred?
Yes.
Let's just
Yes.
call it element 1, situation 2. And I want to ask you, is U4, 1, U4, 2, are they the same or they're different? When you solve use finite element.
They are the same.
They're the same. Okay. So Alfred, do you see the problem now? Do you see a problem now? That is to say that, okay, there's no difference. When solving traction problems on single elements, regardless of the distribution of traction. This is surprising, right? Surprising, right? So Moin, I left the most difficult question to you. What if I want to show the difference between them two? What do I need to do? What do I need to do?
What do you mean? You show what? You want
But
to
right
show
now, right, I have the Q, 2Q, Q, 2Q, they're the same. But
Mhm.
on element 1, I have a linear distribution. On element 2, I have a nonlinear distribution. Now, theoretically, their displacement should be different, isn't it?
Yeah,
But
it
in
has to be different.
FEA, yeah, but in FEA, since we use the same shape function, the nodal forces will be the same anyway,
Mhm.
right? So when we solve the matrices, the displacement we solve for both elements will be the same. And that's now correct. Is that right?
Yeah. Yeah.
So if I want to correct it, what should I do here?
Maybe we could add some nodes in between.
Add some nodes, exactly, right? So I can add nodes. Why can I add some nodes? I can increase my results.
Actually,
What?
yeah.
Yeah, because I have a better accuracy. Why is that? Because there's another very important rule you need to remember. Remember is that on this is rule number 1, this is rule number 2. On the nodes, the FEA solution is what, Moin? Is what? Is accurate. Is that right?
Yeah, on the
Right.
node we have
Yeah.
accuracy.
On outside the node or in between nodes, it's
We have-
approximation.
Yeah, approximation.
Right. Exactly. You got it. Okay. Is approximation. Okay. So Heitherman, you up again. Hytham, sorry. Sorry, I keep
Yes.
calling you Heitherman. Sorry about that. Heitherman. So quick question here. So if I'm dealing with a complex problem, say a concrete plate, okay, I have a very complex stress field due to temperature shrinkage and formwork, what you have it, right? So to increase my accuracy, I need to what? What do I need to do?
For the concrete plate,
Well, it's elastic. Everything's simple as we just talked about it, right? Don't go out to the real, right? Think about what we just talked about it. If I want to have accurate solution, what do I need to do? I what? I increase what?
increase the number of nodes.
I increase nodes. That means increase what? Number of
Meshes.
elements.
Yes, element.
Right. So that is the main reason why we want to increase the number of elements in the first place. Is that when the boundary distribution, when the traction distribution, the boundary stresses are highly nonlinear, we increase the mesh, right?
Yes.
Right. So now you know, right? The reason why we increase the mesh. Okay, so I hope we'll learn something on this. All right. So this is not over yet. This is not over yet. Now we just have stresses. Now we just have stresses, tractions, right? Distribution and everything, right? And I need to compute. I need to compute my elements, right? I need to compute my elements. So how do I compute my elements, right? So I want to leave something, and then I can end the course a bit early today because I have something else that I have to get to it in terms of the FEA project development. Anyway, so now when I have an element like this, okay, when I have an element this is say U1, U2, and this is homework number 2, okay? Homework number 2, U2, U3, U4, okay? And well, sorry, okay, let me just make sure I got it. V1, U2, V2, displacement, okay, U3, V3, U4, V4. All right, and now let's just say that in terms of a nodal displacement y, this is C, this is eta. Okay, and I have all these numbers for you. U1, V1 is 0.5, negative 0.5, and positive 0.25. Okay, U2, V2 are 0.05 and 0.01. Okay, and U3, V3 is more stretching, like say positive 0.5 and positive 0.25. And U4, V4 again is very small number, so minus 0.05 and minus 0.01. Okay, now you have all these values. Now with all these values, right, I want you to do this, okay? I want you to do this. First is that find a displacement U and V at a coordinate system, right? This is a local coordinate system already, right? C equal to, this is ranging -1, 1, this is -1, 1. Clear it up. Okay. I want you to find UV at Xi, and this is Xi and eta, okay? A 0.25 and negative 0.25. So 0.25, negative 0.25, where are they, right? So think about it, quarter. So this is 1, positive 1, so this is like quarter here, and negative quarter here, so this point of interest. I want you to find displacement field at that. So this is homework number 1, 2, okay? And sorry, 2, 1, and second question, 2, is that if I have a distribution of stresses or attractions, okay, like this, and say this is Q, this is 3Q on node 1 and 4, okay, and a linear distribution, right? Linear distribution. I want to find out what is my nodal force F1 and nodal force F4. Okay, is this clear, guys? Any questions on this? Are we okay? Okay.
Yes.
And this homework due date, let's push it because the homework 1, it hasn't finished. You guys haven't finished yet. So let me give more time for you guys. Let's just say, let's do October the 7th. Well, actually, let's do October 8th to make it Friday every time. So it'll be easy for me to grade, easy for you guys to remember as well. Okay. Is this clear, guys? Are we okay on this?
Yes.
Okay. Heiseman, you good? Heisem,
Yes, I'm good.
Jolly and Moy, you guys good?
Yeah.
Okay, Jolly, you
Yes.
okay? All right. So it's a quick hand calculation. Just want you to be familiar with the process, okay? And now if there's a bonus point, okay, you don't have to do this, but it's up to you. If this is the bonus one, what if, right? If this is parabolic, and you probably have to figure out a parabolic interpolation yourself, okay? If Q is a coordinate, local coordinates S is a parabolic, means second order, okay? Okay. Show F1, F4, okay? Also show Q at, if this is length is L, Q at half L. Okay, very simple, Q at half L. Okay. All right, that's it, folks. Not too bad. It's a very simple question. I think I'm just gonna pause here, close here, and we'll continue on Thursday where I can talk to you guys more about the rest of the problem. Okay. All right. So let me stop recording and you can